Okay, let's get started. Let me introduce myself. My name is Chip Fricke. I'm an application engineer with the FEMAP product development group. I'm actually located at a home office in Central Texas. I guess a home office is common for almost everybody these days. So for the next probably 50 minutes, I'm going to do a presentation on the Simcenter Nastran Multistep Nonlinear solution. And I'm really tailoring this to what we support within the FEMAP user interface at this time. There will be some notes as the things that are available, but they're not supported with FEMAP. So my agenda is I'm going to do just a brief overview of multi-step nonlinear. I'll get more details in the multi-step structural, the solution 401. More details on the multi-step kinematic solution 402. Then I'll compare the two solutions. Then we'll open it up to questions and answers. And I believe there's a chat session where you can submit questions as well. So in the past, with Simcenter Nastran, we've relied on the advanced nonlinear solution. This was a third-party product from Medina, but with the acquisition of LMS, they had some nonlinear technology basically through their SAMSEF solver. So in conjunction with those people with all that experience with nonlinear, we've developed the multi-step nonlinear solution, which is solution 401 and 402. 402 is basically still the SAMSEF solver, but it's interfaced through Simcenter Nastran, so you don't need to know the different format for SAMSEF. SAMSEF continues to be developed, but as that's being developed, that's being implemented within the solution 402. Okay, it's through multi-step nonlinear. It's a general purpose nonlinear solution. Multi-step is basically use the traditional Simcenter Nastran architecture and technology. And then again, multi-step kinematic is based on the integration of SAMSEF in Simcenter Nastran. So there are similarities. They use many of the same formulations and give nearly the same results. And the core set of capabilities are nearly the same, and they can be used, basically use both for the same application. Again, you use the same Nastran inputs and outputs, and it's easy to convert one solution to another. There are some differences in setting up the control and the subcases in that, and we'll go through that in more detail later. Again, 402 is better support for nonlinear kinematic behavior. For an example, any very large displacement or rotation applications. I don't know if people remember, at one point we posted an example of advanced nonlinear showing just a simple metal forming application. That would be a better application for solution 402 because you're getting into large deformation and strains and displacement. And solution 401 is used for multi-physics co-simulation. So there are planned commonalities and differences. There's large displacement is supported in both, although 402 is better suited for that. Plasticity, creep, contact, and material models. And again, I'll go through more detail on that a little bit later. And then 401 has the multi-physics couplings, and 402 is a little more robust in composites and in the nonlinear mechanisms. So next I want to get into the 401. So again, you access through the analysis set manager where you would select the multi-step structural solution. In 401, which is much different than the old advanced nonlinear, you can have subcases declared sequentially dependent or not sequentially dependent. So you could really have a start, stop, go back to the beginning, and then continue on from there in one solution. The other thing that's very powerful about 401 is that you can change contact conditions between cases. So you can add contact or remove contact. Also, you can change the iteration control between subcases, and then the analysis type. So for 401, for the master, you could do statics, modal and transient dynamics. And then for subcases, you do the bolt preload. Okay, as far as the element support for 401, in 401 line elements, there's beam, bar, spring damper, and C-bush elements. There's the laminate elements. Now, the one caveat I did want to note is that there is in 401, there's something called a PComp G1 laminate property that allows a different failure theory for each layer. However, we're not supporting it at this time in the FEMAP user interface. There's also the plate, and then there's the plane strain and stress. And then again, plane stress you'd set by element formulation. Then we could do all of the volume elements supported by FEMAP, including the solid cohesive. We'll talk a little bit about that later. We also support mass matrix, the spring damper the ground, the DOF spring the ground, and also the RBE2 and the RBE3 elements. Okay, this little chart just kind of shows you the different types of element types and the material models and the solutions that are supported in 401. And at some point, we'll probably make this presentation available as a PDF, most likely on the FEMAP community site. Also, we have the plate, laminate, and generalized plane strain elements. You can see that the anisotropic is supported for the plate, but not for the laminate and the generalized plane strain and stress. Also, you notice that large displacement is not supported for the laminate in 401. Okay, then you have your solid elements. You can see that that the axisymmetric, basically all of the material models. The other thing I want to point out that in 401 and 402, also the non-linear elastic material is available as well. Okay, so talked about something unique to 401 and 402 are these basically damage or cohesive elements. So they're used to model adhesively bonded interfaces. And it also can be used to model damage. So we have these cohesive elements. So you're basically doing compliance in the connection and in damage in the material. And there's two element types that are supported for this. That's the hex element and the pentagon element. So the 8 and 20 noded, or the 8 noded hex element, and then the 6 noded pentagram. This, you can occupy a solid volume or collapse to a planar area. And then one thing to note from this is that Simcenter Nastran uses the thickness from the property entity, not the thickness based on the grid locations for stiffness calculations. So please make a note of that. There is one exception to that though, and it's based upon what material type you pick. And you have to reference basically what you're creating with this is this P solid CZ property entry. So along with this, there's this MAT CZ or this Nastran cohesive element material or Nastran cohesive material. And you can see you can specify things such as out of plane normal stiffness, in plane stiffness. There's different damage laws. And then there's things like critical energy release that you could set within this cohesive material. Now, just similar to what's with composites or some things like hyperelastic materials, these are generally determined through tests. So we don't really supply a material library for these types of elements. They require a plasticity option, so you do have to turn on the nonlinearity within the analysis set manager, and that is actually on by default when you create a new analysis set for 401. And it could be one of the 3 different types of materials. So you could do a mat 1, a mat 11, or this mat CZ. Now, the interesting thing is, I mentioned before, is that there is an exception to this thickness on the property. This thickness value is ignored for this solid cohesive property if you use this mat CZ. Okay, one of the things when this was added, and I think we added this in either 2012, yeah, it's in version FEMAP V12, I should say, is we did add the ability to do this cohesive meshing, where you basically take an existing mesh and you put in this layer of cohesive elements within the mesh. So you basically pick a set of nodes that you want to split and add this cohesive element. So that's the mesh editing cohesive meshing command. Something else that we added, and this became in FEMAP version 2019.1, is the concept of a connector set. And a connector set could be something, could either be glued or contact. And I like to say it's analogous to a Nastran reference constraint load sets. So you're basically creating a connection set, and then the other thing about these connection sets in 401 and 402, glued can have a different connector property or connector property for glued contact in 401 versus in the regular Nastran sequences where you could only basically use a single glued contact property. So in this case, this screenshot is showing a panel glue, and it's showing the 2 reference sets, which are frame 1 to panel 1 and panel 2. So again, you could do this through the command or just by clicking on connectors and then saying I want to create a new connector set. Where this is also smart enough that it'll only allow you to select those connectors that are defined with a glued property, or if you're doing a contact connection, only those can be selected that have that are assigned a contact property. One thing about Solution 401 is you can specify your glued contact only in the global case, and this is maintained throughout the whole analysis. So in this case, you can see I've got a connector set for contact and then a connector set for glued. And in this case, you actually have the opportunity to select a single glued property. And then in SUBCASE, you can't specify different glued connections, but you can change the connector sets within a SUBCASE. Now, generally, if you're not going to change it, you basically say none. And if you're using a continuous solution or a sequential solution, it'll maintain the previous contact. Now, there are these connection properties. Again, just like we recommend you do whenever you create a new connection property, is use the default settings. There is something unique in 401, and it's called the no separation option. And what that does is once the surfaces or the element faces come in contact, they cannot fly apart. So if you unload it, they retain their contact. So this is, again, unique to 401. For the glued connection, you could, again, use the default. And also something in 401 is something called sliding glue. This allows the surfaces slide one to another, but they cannot separate. So this is a nice little feature of 401. Okay, the master and SUBCASE types again. There's statics, there's normal modes, and then there's transient. And again, the bolt preload is only available in a SUBCASE. And again, you notice when you see the analysis case, you can see you have the option to do sequentially dependent or not sequentially dependent. So if say your master stops at time 2 and you're doing a sequentially dependent, you're actually starting your next SUBCASE at time equals 2. So Buckling is supported by Solution 401. However, we don't support this in the user interface, and you can add this this nonlinear arc control card that equals the subcase ID. And again, buckling has to be either the first or last subcase in the static sequence. Okay, so we have the, so for multi-step control, you set this up in the analysis set manager. The time step and time steps and solution control are set in each subcase. So I'm going to show you, kind of show you the screenshots for a pre-stiffened modes model. So the first one is I'm setting up the master, and what I'm doing is I'm setting up the contact. And in this case, you see I've got the contact connectors and the glute connectors, but I don't have any, there's no boundary conditions in here. Well, actually, I do have this constrained through the lug 1. And you notice that the end time is 0 because I'm just setting up the boundary conditions in the contact. Now in subcase 2, I'm setting up a bolt preload. And in this case, there's something to note when I'm doing a bolt preload under control options, and I'll show the dialog, the control options dialog box. I set up something called skip the nonlinear controls. So this is all handled through the bolt sequence. And there's actually a bolt sequence card that you add where you tell it the number of steps, what bolt loads are, what bolt load case you're using, and the number of steps to use within that bolt case. So this allows you to basically, for an example, let's say I want to simulate I've got 5 bolts and I want to tighten them in sequence and see what happens in the model. So I can have the first subcase do this bolt preload and then go on from there. So the second subcase is I'm going to do some lug tensioning, and I'm basically applying a 100-pound tension load to this model. And now what I'm going to do is I'm going to apply, in the third subcase, I'm going to run the normal modes. So basically this is all sequential. So I'm pre-stiffening with a bolt preload, pre-tensioning with a lug tension, and then I'm applying, then running the normal loads to the pre-stiffened model. Okay, so here's, this shows you the preview of the analysis sets. You can see there's your master in yellow, there's your subcase 1, there's subcase 2 showing statics, and then there's the subcase 3, which is the modes. So that's what your analysis deck's gonna look like for your controls. Okay, again, you can change these control options between cases. So for the bolt preload, I just click this skip NL CNTL, and this will be automatically set for the preload. You can set it auto time stepping. So you have your control of your initial, your minimum, maximum time step. You can set your subcase time step. You can either do new or modify. Here's your equilibrium control. Here's how you can apply your time unassigned loads. So it'll automate, you can set it to ramp or one of the other options. And again, for same thing for time ascent temperature loads. Previously, I talked about how you could do basically this multi-physics solution. So within this, you're basically with the multi-physics, you can simultaneously assign temperatures across the model and loads and solve that simultaneously. You'll also notice you have the ability to assign plasticity and also include creep. So if you're in the linear range, although you're looking at some complex contact, you can turn off plasticity to speed up the solution. Okay, so in this previous one, you notice there's this button called Solution Convergence. And when you click on that button, you get this solution and convergence options. So this is basically setting tolerances for the simulation. The other thing you're doing is you can select the solver in this one. So there's 4 different solvers that are available within 401. There's the sparse solver, which is the default. There's this partitioning solver or partiso. It's faster than sparse, but it's a little less accurate. MUMPS is the one I actually prefer to use. It's a multi-frontal, massively parallel sparse direct solver. So it's still a sparse solver, but it's really tuned to doing multi-processors. And then there's the element iterative solver. And then you can also set up your stiffness parameters and then your convergence parameters. So that's all in your dialog box. And just like we do with all of the other Nastran solution sequences, we set these options in this dialog box to the Nastran defaults. Okay, also there's this ContactBolt preload solution. And so there's some things like there's divergences for a bisection. You set that to 0 to 9. Then there's also some different tolerances. And you notice that the unsymmetric solver is this Paradiso solver. So we recommend that you leave that as the default for doing a bolt preload. And then again, setting your tolerances for the bolts. So nonlinear time steps, this is very similar dialog box to the advanced nonlinear control. You can see you got the end time, number of increments, your output frequency, and then your output increment. So you set this for each subcase, and then you specify the end time and then the increments. Now again, the start time is a function of the case being sequentially dependent or non-sequentially dependent. If it's non-sequentially dependent, your start time is 0. If it's sequentially dependent, your start time is the end of the previous case. So just keep that in mind as you're doing that. Now for bolt preloads, that bolt preload's always gonna end at time step 0. And then you can assign loads can be ramped or stepped as well. So when you set up your boundary conditions, you have two pull downs. One is set up the load that's ramped or versus time. Now in solution 401, you can only do a load versus time function. Now for 402, it's a multi-step structural solution. It has a combination of global and subcase types, just like 401, and it also supports large displacement kinematics. So for global, you could do statics, normal modes, and transient dynamics. And then for your subcase, you could do both preloads, statics, normal modes, transient dynamics, and we also support buckling in the 402 subcases. Now 402 does support cyclic symmetry and Fourier normal modes, but we don't support that in the GUI, so you'd have to do manual deck editing. Okay, 1D elements, just like we support the same 1D elements as 402, the rod, bar, beam, spring damper, DOF spring, but in addition, we also support the gap element in 402. For plate elements, there's the plate, laminate, and plane strain. Now note on the plate elements, the triangle and the quad elements are automatically converted by Nastran to the C-tri-R and the C-quad-R elements. And then volume elements, you've got the solid laminate, axisymmetric, and the solid cohesive. And again, just like in 401, need a hex or a pyramid element for your cohesive. And then we have the mass matrix, the DOFs, the spring damper to ground, DOF spring to ground, and then the rigid elements are supported in 402 as well. And again, it's both the RBE2 and the RBE3. Okay, here's a little chart, or kind of an eyesore chart, I call it, showing the different types of materials that are supported in 402. You notice that creep is supported for basically all of the element types except for the laminate. And then also plasticity, there is some limitation on the plasticity. I'll have to double check. We may support plasticity in 402 for laminate. I'll double check this. Again, for bolt preload, you can only use, oops, that's actually incorrect. It should be a beam instead of a plate element for bolt preload and then the solid elements. Okay, there are additional 402 materials. You have 3 types of hyperelastic materials, the 3 models, the Mooney-Reuland, the Hyperfoam, and the Ogden material. And then there's a viscoelastic material that's available. There's also the cohesive, which is available in 401 as well. And then you have 2 additional ply failure materials available for 401 and 402. There's this UD and the EDU. And there is a complete Nastran nonlinear users guides that do describe these materials pretty well. Okay, contact modeling, you could do solid and beam bolted connections in 402. You could do rigid connection regions. Again, just like 401, glued contact is defined in the master only. The glued and contact connector sets, again, just like in 401, and you can use the designated connectors used in a master or subcase. And your connection properties are a bit different than 401. For an example, the glue does not have that sliding option that 401 has. 402 has some additional options, and including some things like shell element thickness offset. And also it does have something called a large displacement contact formulation. Okay, the analysis set for 402 looks very similar to 401. You have your global requests, and then you have your analysis, your subcases. And again, the subcases can be sequentially or non-sequentially dependent. And then you have several control options. You do notice that you don't really have a option to select a different type of solver like you got in 401. However, you can get into the different equilibrium convergence, time integration options through this iteration and convergence button. And you can see you could also skip these and use the default again, like you do your bolt preload. You just hit the skip the multi-step control or the nonlinear control options, and then the Nastran will figure that out for you. All right. So as far as nonlinear time steps in 402, mechanical and thermal loads can be defined as a function of time in a static subcase. And these time assigned loads can only use time as the mechanism to increment loads. Okay, non-time assigned loads can be ramped or stepped. And then just like in 401 or advanced nonlinear, you specify a end time, number of increments, and the output frequencies. And again, start time is based on a function of being sequentially or non-sequentially dependent. Again, non-sequentially dependent, start time is always at 0. Okay, let's kind of go through a little comparison of the two. Okay, 401 can be used for the multi-physics co-simulation. So you can apply temperatures and co-simulate that way. And then 402 is used to simulate nonlinear kinematic behavior. So if you kind of look at the FEMAP examples, there's that little clip, and we have showed both with slide line, and we also have it available as a 402 example as well. So that's a large displacement example. Okay, in 401, the offset distance for contact regions is on the contact region. In 402, it's at the contact level. So basically at the connector level. 401 contact is automatically takes the half thicknesses of the shells into account. In 402, you have to manually turn that on with the offset parameter. Okay, for bolts, You can't use pyramid or composite bolts for 401 of this, what we call an E-type 3, where the where you set up a bolt region, where you have the option to set up the axis determined by the solver. That is not valid. You actually have to set up a coordinate system and then specify the axis through that. You will get a fatal error, or you'll get a message saying that you need to do a Nastran system cell to do that. Bolt loading sequence is allowed in 401, and then you could do an initial strain bolt preload force in 401 as well. Okay, 402 bolts are activated for the whole subcase time interval. And then in 401, the non-sequential or non-sequential subcase, it always has a start time of 0. And then the dependent static or modal subcase does not use the displacement strain or anything else from the previous static subcase. A non-sequential subcase in 402 uses the final time for the previous subcase for its start time. But the computation state can be ignored or reloaded using something called a R-sub parameter. Okay, we're pretty much at the end. I guess we're going to have lots of time for Q&A. There are multiple examples. We do ship this large deformation for multi-step structural for 401, and then the surface-to-surface contact for 402. Starting with version, I know that when Nastran version 12 came out, that the multi-step nonlinear user's guide was very sparse. You pretty much had to go to the release guide to get 402, but that has been updated. It's a much more robust user's guide. And then there are examples in the Nastran support demo and TPL DAT files. In fact, when you search for it, you'll actually see like 401 or 402 in the file name for those. So before we get into Q&A, we'll get into Q&A. So if you have additional questions on the material covered today, you should contact Andrew Jabola. I'm sure SDA customers are very familiar with Andrew's support. And then if you've got questions about pricing or to see a demo, you should contact Keith. So let's see how I need to turn on. Let's take a look see if we can look at the questions here. Okay, here's the questions pane. Okay, here's the one question. Is there support for external super elements in 401 or 402? No, there is not at this time. Let me just do it, just to confirm that, let me just flip over to FEMAP. Oops, I need to unfreeze my screen here. Let's see here. Let me flip over to FEMAP. Let's move this off to the side down here. So I'm going to go in and create a new analysis set. So let's do new. Let's do the multi-step structural. Yes, it does look like you can restart a previous analysis. So you can start from a regular Nastran. However, you notice that you don't have the ability to save the databases in 401. So you can only say like a restart from say like a linear statics, or maybe you got a complex heat transfer. You could restart from that previous analysis, 401. Let's look at a new 402. And let's go next. And again, just like in 401, I can only do a restart in 402. So I can't do a restart, but again, the question, I guess, was I got a little bit off the subject there. Let's take a look at the options for 401 again. Let's look at bulk data. Yeah, I do not see an option for super elements in 401 or 402. So at this point, I don't think there's any support for that. It may be in an upcoming Simcenter Nastran release. I guess I'll have to submit that to those folks and see if that's going to be supported in a future release. Okay, are there any other questions? We've got several more minutes. Okay, let me, so what I'll do is bring this slide up again. So again, if you've got technical questions, please email Andrew. We do work very, Andrew, I guess he's out on a project now doing real work, but he'll be happy to respond to your questions on the advanced. Now it looks like we've got another question here. Okay, okay, are there any significant features that exist in 601 that we should be aware of? There's really not. I don't believe there's anything that's missing in 601 that's it, or in 401 that's in 601. The big difference between in 701 is basically the explicit solver. At this point, 401 or 402 does not have the capabilities. Basically, you really can't do high-speed dynamics with 401 or 402. So that's really the big difference between the multi-step nonlinear and the advanced nonlinear is you can't do the high-speed dynamics. Okay, so somebody wants to see a brief demo with an example. All right, actually, I've got one here. This is that model that I show, or that screenshot I showed before, the analysis set. This is actually this pre-tension bolt loading or loads. So what I'll do, since I've got time, is I'll show a little walk through the model. You can see I basically have two materials. I have an aluminum, and then I have my bolts made with a stainless steel. I basically just set a separate property for the two lugs, and then I've got the bolt. Now what I did is I do have the bolt. Let's turn off my results here. Let's turn off my lugs. I do have the bolt modeled as one solid piece. So this is, instead of having a separate nut washers, this is all one coincident mesh because it's all the same material. However, if I start looking at my contact here, my connections, you see I've got my contact property. Let's take a quick look at that. You can see I've basically just got the defaults. I've got a search distance of 0.25 inches. I'm in working inches. If I look at my my glued, you notice that I have a sliding glue, and the reason I did that is I have my washer. So if I look at my two washers, if I looked at my glued connection set, I basically have the sliding of the washers that are on the lugs. So I'm allowing that bolt to shift within the hole, but I'm still maintaining the contact, the glued contact on where it connects to the lugs. And so I have multiple regions in here. So I just kind of walk through this. Here's got my my different bolt holes, my washers where the lugs at the washers. Here's my bolt 2 shaft. Here's my bolt 1 shaft. Now, as far as the bolts themselves, if you look at this here. So you notice that you could define these both by elements or by nodes. For some reason, I didn't reference. Well, you don't need a reference node really for elements. If I did elements, you do need a reference node. And in this case, I did specify a bolt axis coordinate system. And let's see if I could turn those on if I've got those in there. Nope, I don't. actually have that in that group. So let me just add those to the group. We do coordinate system ID. Add those to that group so we can see them. Okay, so I have two radial coordinate systems that are defining each of the bolts. And then I have, here's my, again, I showed you these contact connector sets. So you can see these two. So here's my contact connectors, and then there's the glued. As far as loads go, let's take a look, go back to my model. I just have a couple load sets. I've got a pre-tensioning of a bolt or on the lug, and then I've got my bolt preloads. So with the bolt preloads, I just use the force. Basically, it's equivalent, I think it's like equivalent to 250 pounds or 250 inch-pounds of torque on the bolt. And then I've got really the only function I did have a load versus time function, didn't do that. Let me show my full model here. And let's go turn on my properties as well so we can see those. And my loads and constraints. So you can see I've got pinned holes here, and I have for the preload, I've got bearing loads. Okay, this is a good point here. Let's see, are there any highly dotted for to explain the contact settings? The documentation for the contact settings, you should refer to the Nastran multi-set nonlinear users guide. And then there's a difference between no separation and sliding contact. Again, no separation means for contact, for contact, it means once the two surfaces come into contact, they can't split apart. So it's almost like you're gluing them. You're like looking at the gluing operation, pushing them together and gluing them, and they can't come apart. Now, for sliding glue means that they're basically in compression, but they can slide relative to one another, but they can't come apart. So that's the difference between the no separation and the sliding glue. So let me go back to my group that's showing the section view. Let me click to my front view here. Let's align it with there. So if I go to my post, let's just kind of, again, this is here's my pre-stress for preloading the bolts. Let's look at my deformed shape. Let's go to actual. That's a little bit way out of line. So this is a factor of 10 to 1. You can see there's the bolt preload. Now let's go applying the tension. Let's go to about 20% or about 30% of the pre-tensioning load. And then what I could do is let's turn off my contours for the modes. You can see I've got multiple modes here. So here's my first mode. We'll go back to percent of model. So here's my first mode shape, and I'm going to turn on the full model again. And I can turn off my, so that's my first mode shape. It's my second mode shape. Again, this is the preload bolts and a lug tensioning. So you're seeing the different mode shapes based the first 10 mode shapes based on that. So this is actually quite interesting when you can see the twist in this model, these different mode shapes. And again, you can see because I've got contact, there's your modes. There you go, there's mode 10. There's your mode. Now again, because this is percent of model, it's showing interference. It actually should not be. I guess I'll have to investigate that if that's, let's go to actual and scalable one. Yep, that's hard to tell from that. Yeah, there looks like I've got a little problem in the model right with that last mode with the contact. So I'll have to investigate that one. So that's a little step through the model. Let me just see if I could get my. Let me pull up a. Let me look at my Scratch file. I can tell you how long this took to run. I just actually ran this. So here's my log file. This ran in, well, it says an hour and 21 minutes. So this took some time to run, and part of it may have been because I did use 100 time steps for the bolt pre-tensioning. Let me get out of this. See, do we have any more questions? Nope. So I think we're about 12 minutes before the end of the hour. Looks like we have no more questions. So thanks for everybody for attending this, and hopefully you'll get a chance to try out the 401 402.
I appreciate it. Thanks, Chip. This is Keith Brennan. If anyone has any questions on the 401 402 solution, please feel free to reach out to me, either by phone or email me.
All right, thank you, everybody.
Thank you. Everyone have a nice day.